Hello and welcome to Common Core Geometry by eMATHinstruction. My name is Kirk Weiler and today we're going to be starting Unit 5. Now Unit 5 is called the Tools of Coordinate Geometry. So far we've explored geometry through the use of transformations, specifically rigid body motions, and through Euclidean geometry logic. But today what we're going to be doing is start to use the Euclidean plane or the Cartesian coordinate system in order to explore different phenomena that we've already seen in geometry. Specifically, today we're going to look at the connection between the slope of a line segment and whether two line segments are parallel or not. So let's get right into that. In our first problem, we're going to explore and review simply how to calculate the slope of a line. Now specifically, exercise 1 says, two line segments AB and CD are shown graphed below. Determine the slope of both of these lines graphically. Recall that slope is the ratio of the rise of the line to the run of the line as we move from right to left along the x-axis. Now this is exceptionally important. Whenever you read a graph, you want to read it going from left to right. And what that will always ensure is that the run, the horizontal change in the line, is positive. Therefore, we only have to worry about whether the rise is positive or negative. Let's jump right in and take a look at segment AB. Now we see automatically that AB is rising as we go from the left to the right and therefore should end up having a positive slope. But let's calculate those rise and run. All right, let's get ourselves a little bit of color in here. Okay, and really what we're thinking about is as we move from point A to point B, how much horizontal distance do we move? That's the run. And how much vertical distance do we move? That's the rise. In this case, we can simply count, and the rise is 5, and the run is 10. So, if we come over to here, we can simply say, our line went up 5 units between A and B, it ran 10 units, and the ratio of the rise to the run is 5 to 10, which we can reduce by dividing both numerator and denominator by 5 to get 1/2. Now, one of the neat things about reducing slopes down, besides the fact that you can see them in their simplest form, is that you can also see that reduced form literally on the graph. Let's take a look at the graph one more time and see if we can zoom in on it. Hopefully we can. Sometimes that's not so easy with the board, as it's not turning out to be here. All right, we're not going to zoom in apparently, but let's take a look at something. All right, remember, we reduced that slope down to 1/2, and what we can see is that if we just take a look at all the points that lie at integer locations along this line, to go from one point to another, we're moving 2 to the right and 1 up, right? We can see that reduced slope in that 2 movement to the right, 1 movement up, the ratio of rise to run. Let's take a look at the other line segment. Now immediately we see that line segment CD is falling as we move from point C to point D. Again, always read that graph from left to right. But let's get those rise and run numbers. Okay, now in order to go from C to D, I think we'll just stick in red here to contrast the two lines. We need to run a total of 8 units. But we don't have a rise now, we technically have a fall. And what do we have? We've got 3, 5, 8, and 12. I'm going to actually label it as -12 right there. Somehow I've lost my pen. Let's get it. There we go. -12. So our rise is a -12 units. Our run is a positive 8 units, so the ratio, -12 to 8, is the slope. We can again reduce that down. That ends up being a slope of -3/2 in simplest form. Again, what that means is that for every 2 units we move to the right, we will drop 3 units in the vertical direction. Slope is always telling us a direction that we move in terms of how much right-left and how much up-down. Let's go on to the next topic. We don't want to always have to calculate slope graphically. It's nice when we can, but we want to be able to do it if we simply know the coordinates of the points that we're looking at. So if we know that we have 2 points generically labeled as x1, y1 and x2, y2, we can calculate the slope with this famous formula. The slope is the change in y over the change in x, y2 minus y1, divided by x2 minus x1, or you can flip-flop those points, just make sure to keep the rise in the numerator and the run in the denominator. Make sure you understand why the slope formula works. Never let a formula just kind of sit there without understanding it. You see, what we really have going on here is we have a right triangle. The run is given by simply taking these 2 x coordinates and subtracting them, and the rise is given by taking the 2 y coordinates and subtracting them. This allows us to calculate the slope of a line segment if we know its 2 endpoints without having to plot the line segment. And let's do that a little bit in the next exercise. All right, real kind of plug and chug exercise here. We've got 3 different situations where we've got coordinate points and we want to calculate the slope. Let me read the problem to you. Exercise 2. Using the slope formula only, find the slope of the line segment that has the following endpoints. Write your slope in simplest form. All right, let's jump in. I'm going to do letter A, then I'm going to have you work on letters B and C on your own, and then we'll go through them. First, let me go back to blue ink, and let's do this. Simple enough, right? It never hurts to write down a formula when you're first using it. Slope, which we, for some almost inexplicable reason, give the letter M. I think of that as M for movement. Is y2 minus y1 over x2 minus x1. It doesn't matter which of the 2 points you designate as x1, y1 and x2, y2, but it'll be natural to think about that first one as x1, y1 and the second one as x2, y2. Let's get back into the calculation. So here we go. If this is x1, y1, and this is x2, that almost looks like a 2, but not really, y2, then we can write down our calculation as follows. 10 minus 4, all divided by 8 minus, be careful here, negative 2. Now 10 minus 4, simple enough, is 6. Don't forget that when you subtract a negative, it becomes a positive. So 8 minus negative 2 is going to be positive 10. We reduce that to simplest form, and we get a slope of 3/5. Indicating again that for every 5 units we move to the right, we're going to move 3 units up along this line segment. Now what I'd like you to do is take a few minutes, pause the video if you need to, calculate the slopes in letter B and C, and then unpause the video when you want to see the work done by me. All right, let's go through letters B and C. I'm not going to write the formula out again, I'm just going to do the calculation. In letter B, we have the slope is y2, negative 9, minus y1, 3, divided by 11, minus negative 10. All sorts of things can trick you up on things like this with the sign numbers. Negative 9 minus 3 is negative 12, and 11 minus negative 10 is positive 21. If we reduce that by dividing both numerator and denominator by 3, we'll get a slope of negative 4/7. Let's do letter C. In this case, our slope will be y2 minus y1, 3 minus 11, divided by negative 2 minus 2. Be careful, that's not going to be a 0 in the denominator. Not yet, at least. 3 minus 11 is negative 8. Negative 2 minus 2 is negative 4. Negative 8 divided by negative 4 is positive 2. A lot of people like to express their slopes as fractions so that they can think about rise and run. Obviously 2 is just an integer and you can leave the slope as 2, or you can express it as 2 divided by 1. Thus being able to think about it as moving 1 unit to the right while moving 2 units up along this line. It is critical in this unit that you're able to accurately and quickly calculate slopes, not making common mistakes like putting the change in x in the numerator and the change in y in the denominator, and also all of the little numerical mistakes that can happen with signed numbers. Be good about these calculations. If you have to use your calculator, bring it in to check your work at the very least. Let's move on to the next exercise. All right. Here, we want to make the connection between slope and parallel lines. It's an easy connection. It's one that you already know in all likelihood, but it's one that's going to be very important in this unit. So let's take a look at it. In exercise number 3, it says, in the diagram below, the two pairs of parallel lines are shown. Letter A asks us to name the parallel line pairs. I bet you can do this for yourself, so take a moment and try to name the two pairs of lines that are parallel to one another. All right, let's go through it and make sure that we review how to use the parallel line symbol. It's pretty obvious to me that line M is parallel to line S, so that's one pair, and line N is parallel to line R. That's the other pair, right? But now we want to make the connection to slope, and that's going to occur in letter B. In letter B, it says, for each pair, determine the slopes of the two lines that make up the pair. You can do this graphically or algebraically. For me, because I have the graph simply sitting here, I'm going to do it graphically, and I'm going to do both of them together, but take a minute and try to figure out the slopes of both of the lines for yourselves before we pick it back up. All right, let's get back into it. So let's do line M, okay? If we look at line M and we pick any given easy point on it, what we can see is that we need to go 3 units to the right and 2 units up each time on that line, at least in order to go between 2 nice points. And therefore its slope, rise over run, M and M, that's okay, we'll live with that, is going to be 2/3. Let's take a look at the slope of line S, the line that it's parallel to. What we see with line S is that we also move 3 units to the right and 2 units up between each of the 2 points that are consecutive on the line. And so its slope is also 2/3. All right, let's take a look at lines N and R. Now again, I hope that just by looking at the picture, you can tell that lines M and S have positive slopes and lines N and R have negative slopes. But let's do N and R, okay? For line N, what we find is to go from this point to this point, we would move 2 to the right, but we would have to go 5 down. So its slope is going to be -5/2. On the other hand, that was actually line R. My apologies. Let me erase that. That was line R. Line N, well, it looks like it's the same thing. We're going to go 2 units to the right, 5 units down, so its slope is also -5/2. All right, now of course the most important connection of the lesson is in letter C. Let me read that for you. In letter C, it says, from this exercise, what seems true about 2 lines that are parallel? Well, see if you can write down an answer. Just from this exercise, what do you think is true about 2 parallel lines? Well, it appears that 2 parallel lines have the same slope. So let's write that down. Two lines that are parallel let's use a nice mathematical term for it, have equal slopes. At least that's what it appears, and that is in fact true. Let's summarize on the next slide. Slope and parallelism. 2 non-vertical lines will be parallel if and only if they have the same slope. Now, a couple little explanations in that mathematical jargon. Number 1, why do I have to throw this in? 2 non-vertical lines. Well, what we'll see a few lessons from now is that you can't quantify the slope of a vertical line. So you can't really say that two vertical lines have equal slopes because vertical lines won't have a slope. But don't worry about that for right now. That's kind of a side case. We don't have to worry too much about vertical lines. But then the if and only if piece. Let's talk about that just for a moment. What that means is that parallelism and slope, it's a mighty big word, parallelism and slope, they're a two-way road, meaning that if two lines are parallel, they have the same slope. And if two slopes are equal, then that indicates parallel lines. It works both ways. Again, if I've got this blue line and this red line that are parallel, and this one has a slope of 1/3, then this one somewhere will also have a slope of 1/3. Or maybe it won't. There it is. I couldn't find the hidden slope. Slope will tell us whether things are parallel or not. And let's see that in the last exercise. All right, exercise number 4. Given points A, B, C, and D, do the following. Letter A asks us, is AB parallel to CD? Give evidence to support your answer. Well, for us, it's never going to be sufficient to just draw something out on the coordinate plane and say, well, they look parallel. We're going to have to use calculations, the tool of the slope calculation, in order to see whether or not these two line segments are parallel. But that's simple enough. What I'd like you to do is take a moment to calculate the slope of those two line segments and see what you would conclude. All right. Let's get into it. Let's make sure we're very good about our work. We lay it out so everybody knows what we're doing. Line segment AB. Let's do it. The slope of line segment AB will be 7 minus 1 divided by 6 minus negative 2. That's going to give us a 6 in the numerator, an 8 in the denominator, for a reduced slope of 3/4. Let's take a look at CD. The slope of CD is going to be 6 minus, we have to be careful here, 6 minus negative 3 divided by 8 minus negative 4. 6 minus negative 3 is positive 9. 8 minus negative 4 is positive 12. And if we reduce that, it becomes 3/4. I want to step back just for a moment and talk about this. This is one of the primary reasons we want to reduce fractions, especially when we're doing slope calculations. Initially, a slope of 6/8 and 9/12, they may not look like they're equal. But when we reduce them both to 3/4, we realize those two ratios are the same, and we can now say, yes, what? Yes, AB is parallel to CD because slopes are equal. Little abbreviation, but that's completely okay. Now we're asked the same thing in letter B except for two different line segments. Letter B asks us, is AC parallel to BD? Again, what I'd like you to do is pause the video right now and work through it to see what you find. Okay. Let's go through the calculations. Now we have to be a little bit careful because now we're calculating the slope of AC and points A and C aren't sort of sitting right beside each other in the problem. But that's simple enough. We just have to keep track of everything. We're going to have a slope of negative 3 minus 1 all divided by negative 4 minus, be careful, negative 2. Gives us negative 4 in the numerator. And it gives us negative 2 in the denominator, which gives us a positive 2 when we reduce it. On the other hand, BD, let's take a look at it. It's going to have a slope of 6 minus 7 in the numerator and 8 minus 6 in the denominator, which is going to give us negative 1 in the numerator and 2 in the denominator. These two slopes aren't equal. And again, the connection between slope and parallelism is solid. If these two slopes aren't equal, then these two line segments can't be parallel. So absolutely not. No. Slopes are not equal. Okay. Now, the final part of this problem is the most challenging one, because in parts A and B, all we had to do is do a couple slope calculations and then compare the numerical results we got to see if the two line segments were parallel. But let's take a look at letter C. If point E exists such that its x-coordinate is 12 and ED is parallel to AC, then what is the y-coordinate of point E? Show how you arrived at your answer. Well, I'll tell you, geometry and highlighters go together great. So if you can ever do this and you've got a highlighter handy, which apparently I don't, here it is. Nice highlighter handy. And you see some statement like this, ED is parallel to AC. Highlight it immediately, right? That's going to be the key to doing this problem. In fact, right, if we go back to it, what that's going to tell us now is that the two slopes must be equal. All right? Well, what do we really know about point E? Right? We know point D, it's up there at 8, 6. But point E, all we really know is that its x-coordinate is 12, and we don't know its y-coordinate. We do know point D. I'm going to rewrite it right down here so that we've got it right in our view. And we know the slope of AC. So let me write that down here as well so that we've got it just handy. The slope of AC was 2. Now the question is, how can we use all of this information to find the y-coordinate of point E? Pause the video and challenge yourself with this problem. Unpause the video when you want to see the solution. All right, let's go through it. We know that the slope of line segment ED is going to have to be equal to 2 because ED is parallel to AC. Let's set up the slope for ED. All right, it should be simple enough. After all, even if we don't know the two coordinates, its slope still has to be y2 minus y1 over x2 minus x1. Okay? And we know, because these two line segments are parallel, that must be equal to 2. And what we now have is we now have a very convenient algebraic equation to solve. You could do it by guessing and checking, but let's actually just use some algebra. First things first, let me simplify that denominator, 8 minus 12, to be negative 4. Now we just have to solve for y. I'm going to multiply both sides by negative 4 in order to get rid of that negative 4 in the denominator. That'll give me 6 minus y is equal to negative 8. I'll subtract a 6 on both sides. Be careful of all the negatives. They're everywhere. I get negative y equals negative 8 minus 6 is negative 14. And of course, if negative y is equal to negative 14, then y must be 14. All right? So if you got the y-coordinate of point E as 14, then you were certainly doing something right here. All right? Now, one of the nice things about getting a result like this is that we could certainly check it. So if I went back to this problem, let me change into red just so that we have a little bit of a contrast. And instead of having a y there, I had a 14. You could now easily calculate the slope of ED by doing 6 minus 14 divided by 8 minus 12. That would give me negative 8 in the numerator, negative 4 in the denominator, positive 2. That's exactly what I needed to have, given that that was the slope of line segment AC, and therefore I know my answer is correct. All right. So what did we really learn today? Well, we reviewed how to calculate slope and its graphical meaning as rise over run. We saw the classic slope formula y2 minus y1 divided by x2 minus x1. And then we saw how slope combines with parallelism, i.e. if two lines are parallel, their slopes must be equal, and if two slopes are equal, then the lines must be parallel. We're going to be using that and many other coordinate geometry tools as we move along in this unit. Make sure that you really work hard again to master the slope formula, and we'll see more tools of coordinate geometry in our next lesson. Thank you again for joining me for another Common Core Geometry lesson by eMATHinstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.